Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. In this episode, we will explore WISE 08550714, or W0855 for short. This sub-brown dwarf is located 7.43 light-years away from Earth, making it the fourth closest known star or brown dwarf system to the Sun. Considering Alpha Centauri is a triple star system, Barnard's star is a single star system, and Lumen 16 is a binary star system, W0855 is the seventh closest known planet or star to the solar system. In the night sky, W0855 is located within the constellation of Hydra, roughly in between the star Alphard, or Alpha Hydrae, and Messier 48, or M48, also known as NGC 2548, a well-known cluster of stars in Hydra. The region itself can be seen from all populated areas of Earth around March. This region is relatively close to the galactic plane of the Milky Way, but not directly within the most densely populated regions of the galactic center or arms. When looking in the direction of W0855, you see a sky with a moderate density of stars. If you were to observe this area with a telescope, you would see a relatively dark and sparse region of space compared to other parts of the sky, especially those closer to the center of the Milky Way. The stars in the field would be faint, with no particularly bright objects dominating the view. The region surrounding W0855, while part of the galactic plane, would appear more subdued, reflecting the nature of the outskirts of the Milky Way's disk. W0855 was discovered in 2014 by Kevin Luman using data from the Wide Field Infrared Survey Explorer, WISE. Unlike Lumen 16, which was also discovered by Luman around the same time, W0855 has not been assigned any other name than its shorter form of the so-called phone number designation. W0855 is classified as a sub-brown dwarf. Unlike stars, which shine due to nuclear fusion in their cores, sub-brown dwarfs like W0855 are objects that never accumulated enough mass to ignite hydrogen fusion. With a mass estimated to be between 3 and 10 times that of Jupiter, W0855 is too massive to be considered a planet, but not massive enough to be a star. This places it in a category of objects that blur the lines between planets and stars, often referred to as failed stars. Brown dwarfs, a subset of substellar objects, do fuse deuterium, a heavier isotope of hydrogen, early in their lives, but this fusion is short-lived. As a result, brown dwarfs gradually cool and fade over time, emitting only the residual heat from their formation. W0855, being a sub-brown dwarf, is even cooler and dimmer than typical brown dwarfs. With an estimated surface temperature of around 285 Kelvin, W0855 is the coldest known brown dwarf, cooler than any other object of its type found in interstellar space. 285 Kelvin is roughly equivalent to 12 degrees Celsius, or 53 degrees Fahrenheit. That is, a temperature which is in itself quite comfortable for humans and other life as we know it. This temperature is closer to that of the Earth's surface than to any star, making W0855 a unique laboratory for studying atmospheres under conditions similar to those on the outer planets of our solar system, like Jupiter and Saturn. The WISE mission made the discovery of W0855 possible by surveying the entire sky in infrared light between 2009 and 2011. Infrared observations are crucial for detecting cold objects like W0855, which emit very little visible light but can be bright in the infrared. After its initial detection, follow-up observations were conducted using the Spitzer Space Telescope and the Gemini North Telescope, helping to confirm its distance and characterize its physical properties. Spectroscopic observations have revealed that its atmosphere is dominated by water vapor and methane, similar to the gas giants in our solar system. However, unlike Jupiter and Saturn, W0855's atmosphere shows no signs of phosphine, a molecule that is present in Jupiter's atmosphere. This absence suggests that W0855's atmospheric chemistry is different, possibly due to its cooler temperature or a different formation history. The atmospheric composition of W0855 is like any object with an atmosphere complex and still not fully understood. Infrared observations have shown evidence of clouds in its atmosphere, possibly composed of sulfides and water ice. These clouds may play a role in the object's weather patterns, similar to the cloud bands seen on Jupiter. However, the exact nature of these clouds remains a subject of ongoing research. The classification system for Y dwarfs is still relatively new and evolving, as these objects are on the edge of what can be detected and classified with current technology. W0855 is classified as a Y4V spectral type object, which is part of the Y dwarf classification, the coolest class of brown dwarfs currently known. The Y dwarfs are characterized by extremely low temperatures compared to other stars and even other brown dwarfs. The Y4 subtype is one of the coldest categories within the Y class. The 4 inches in Y4V indicates a specific subclass within the Y dwarf category, which reflects the extreme coolness of the object. As mentioned, for W0855, the estimated temperature is around 285 Kelvin, 12 degrees Celsius or 53 degrees Fahrenheit, or lower, down to about 225 Kelvin, minus 48 degrees Celsius or minus 55 degrees Fahrenheit. The V in Y4V indicates that W0855 is classified as a dwarf star, specifically a main sequence star in stellar classification systems. However, because W0855 is a sub-brown dwarf, it does not undergo hydrogen fusion like typical main sequence stars. The designation V is more traditional and reflects its status as a low luminosity object that would lie on the lower end of the main sequence if it were a star. As a Y4V object, W0855 has likely cooled significantly since its formation. Since brown dwarfs like W0855 do not have sustained nuclear fusion, most energy comes from the gradual release of gravitational contraction energy. Over time, this energy decreases, leading to a steady cooling process. Apparent magnitude is a measure of the brightness of an astronomical object as seen from Earth, with lower numbers indicating brighter objects. The apparent magnitude of W0855 is of course well beyond the reach of naked eye observation and requiring sensitive infrared telescopes for detection. It also depends on the wavelength at which it is observed. The most reliable measurement for W0855's apparent magnitude comes from the W2 band of the WISE telescope, centered around 4.6 micrometers in the infrared. In this band, W0855 has an apparent magnitude of about plus 14. For comparison, the human eye can generally see stars down to an apparent magnitude of about plus 6 under ideal dark sky conditions. Even within the category of brown dwarfs, W0855 stands out as particularly faint. Observations using the Spitzer Space Telescope in other infrared bands have provided similar measurements, with slight variations depending on the exact wavelength. In general, W0855 is faint across all observed infrared bands, consistent with its extremely low temperature and luminosity. Variability in W0855's infrared light has been observed, indicating that its atmosphere is dynamic and possibly subject to weather-like processes. The variations are relatively small in amplitude, suggesting that the differences in cloud coverage across its surface are not extreme. This is in contrast to some brown dwarfs, which show larger variations in brightness due to more pronounced cloud patterns. In terms of its motion through space, W0855 has the third highest proper motion of any known star or brown dwarf, trailing only Barnard's star and Kapteyn's star. Proper motion refers to the apparent movement of an object across the sky relative to more distant background stars, caused by the object's actual motion through space. W0855's high proper motion is a clear indication of its proximity to the solar system. Another related indicator is, of course, the very large parallax, a phenomenon where an object appears to shift position against more distant background objects as Earth orbits the Sun. The radial velocity of W0855, the component of its motion toward or away from us, has not been well determined due to its faintness and the difficulty in obtaining precise spectroscopic data. However, its large proper motion suggests that W0855 is moving relatively quickly through space. The direction of W0855's movement can be described as generally moving in a direction that would cause it to pass relatively close to our solar system, though it is already past its closest approach. It is not clear whether W0855 it formed like a star, through the collapse of a gas cloud, or like a planet, through the accretion of material in a protoplanetary disk. Its low mass and cool temperature suggest that it might have formed in a way more akin to the gas giants in our solar system, but without a parent star to orbit, it must be either a rogue planet or a failed star. It has most likely, however, formed similarly to stars, through the collapse of a fragment of a molecular cloud. It then did not accumulate enough mass to ignite hydrogen fusion and remained a sub-brown dwarf. The high velocity of W0855 in any case suggests that it might be a runaway object, possibly ejected from its original birth cluster or binary system due to gravitational interactions. This ejection could have occurred in the early stages of its formation. While W0855 now appears to be a solitary object, it is possible that it originally formed in a region with other stars, brown dwarfs, or sub-brown dwarfs. In star-forming regions, multiple objects often form together, but gravitational interactions can lead to some being ejected, as might have been the case for W0855. However, no specific companion objects or remnants of a cluster associated with W0855 have been identified. Its current isolation suggests that, if it did form alongside other objects, they are no longer nearby, or they may have dispersed across different parts of the galaxy. Now, what do we know about the metallicity and core of W0855? The metallicity of an astronomical object refers to the proportion of its material that is made up of elements heavier than hydrogen and helium, often referred to as metals in astrophysics. For stars, metallicity is typically measured relative to the Sun, with the Sun's metallicity serving as a baseline. In the case of sub-brown dwarfs like W0855, determining metallicity is more challenging than with stars, due to the object's very cool temperature and faintness. These characteristics make it difficult to obtain the detailed spectral data needed to analyze the presence and abundance of heavier elements. However, some general points can be made about the metallicity of objects like W0855. The metallicity of a sub-brown dwarf would typically reflect the composition of the molecular cloud from which it formed. In regions of the galaxy where stars and brown dwarfs are forming, the metallicity can vary, but it generally increases with each successive generation of star formation, as heavier elements are produced and dispersed by supernova. Metallicity can influence the appearance of certain spectral features in brown dwarfs, particularly those related to molecules that contain heavier elements, like carbon, oxygen, and sulfur. For example, the presence and strength of absorption bands from molecules like water, H2O, methane, CH4, and carbon monoxide, CO, can be affected by the object's metallicity. Objects like W0855, which are among the coldest known brown dwarfs, are expected to have atmospheres dominated by molecules like water vapor, methane, and potentially ammonia. The relative abundances of these molecules and the detection of any other elements could provide indirect information about the object's metallicity. However, due to the difficulty in obtaining high-quality spectra from such faint and cool objects, precise metallicity measurements for W0855 are not currently available. Given that W0855 is estimated to have a mass between 3 to 10 Jupiter masses, its surface gravity is expected to be relatively high compared to that of planets, but lower than that of stars, or more massive brown dwarfs. For a rough comparison, Jupiter's surface gravity is approximately 2.5 times that of Earth's gravity. W0855's surface gravity would be expected to be similar or slightly higher, depending on its exact mass and radius. For instance, if W0855 has 5 Jupiter masses, its surface gravity could be around 2.5 to 5 times that of Jupiter. The high surface gravity of W0855 would lead to significant atmospheric pressure at its surface or outer atmospheric layers, influencing the structure and composition of its atmosphere. This could contribute to the formation of clouds, such as those of sulfide and water ice that have been suggested in observations. The escape velocity from W0855 would also be considerably high due to its strong gravity, making it difficult for gases to escape from its atmosphere, which is one reason why sub-brown dwarfs and brown dwarfs retain thick atmospheres over long periods. So the temperature is quite comfortable on W0855, and the gravity is high, but not as high as in stars. Would it be possible to imagine any life form in the atmosphere of such a substellar object? Or is the environment impossible to even think of as suitable for an alien life form? The idea of life in the atmosphere of a substellar object like W0855 is certainly a fascinating thought experiment, though it ventures deep into the speculative realm of astrobiology. To explore this idea, let's consider the key factors that influence the habitability of an environment: temperature, gravity, atmospheric composition, and energy sources. The temperature of W0855 is indeed within the range where liquid water could potentially exist under the right conditions. This range is cold by Earth standards, but not extreme in a cosmic sense. The existence of water clouds and potential ammonia clouds in its atmosphere suggests that some form of chemistry, possibly involving water, could occur. The gravity on W0855, while higher than on Earth, is not prohibitive. High gravity could influence the structure of potential life forms, favoring more robust, compact organisms. However, the surface gravity is not so extreme that it would necessarily prevent complex chemistry or even the theoretical development of life. When it comes to the atmospheric composition, W0855's atmosphere is dominated by gases like methane, CH4, water vapor, H2O, ammonia, NH3, and carbon monoxide, CO, as well as potentially other complex molecules. This chemical richness, combined with the presence of water clouds, could, in theory, provide a medium for life, particularly extremophiles, organisms that thrive in extreme environments compared to what is normal on Earth. However, the atmosphere is likely dominated by reducing conditions, which are not conducive to the oxygen-based metabolism that most Earth life relies on. Instead, if life were to exist, it might resemble extremophiles that utilize methane or ammonia in their metabolic processes, similar to certain microbes on Earth that thrive in extreme anaerobic environments. A critical challenge for life in W0855's atmosphere would in any case be finding a stable and sufficient energy source. W0855 lacks a significant internal energy source like hydrogen fusion, and it receives no stellar energy, making it globally cold and dark. The energy available would come from the residual heat of its formation, and possibly from chemical reactions in its atmosphere. On Earth, life often relies on sunlight, photosynthesis, or chemical energy, chemosynthesis. In W0855's case, any hypothetical life would need to rely on chemosynthesis, using chemical gradients or reactions in the atmosphere as an energy source. This would be a much more limited and challenging environment compared to the energy-rich environments on Earth. While the idea is speculative, the possibility of life in W0855's atmosphere cannot be entirely dismissed. Some astrobiologists propose that life could exist in the atmospheres of gas giants or brown dwarfs, where floating microbial life forms could, in theory, survive in the upper layers of the atmosphere, where conditions might be less hostile. All in all, the specific conditions on W0855 make it a highly improbable environment for life as we understand it. Even if life were possible, it would likely be very different from anything on Earth, potentially existing as simple microscopic organisms adapted to survive in cold, chemically rich atmospheres. W0855 is a prime candidate for future observations with the James Webb Space Telescope, JWST, and has in fact already been observed. With its advanced infrared capabilities, JWST will be able to probe the atmosphere of W0855 in greater detail, potentially detecting more molecules and providing a clearer picture of its atmospheric structure. One of the key goals of these observations will be to understand the hydrological cycle on W0855, including the role of clouds and precipitation in its atmosphere. If you are still awake and want more content, go ahead and check out our other episodes. And if you want to help creating even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now, thank you for joining this trip, and have a beautiful and wonderful night, with sweet dreams once you get there.